Hi, I'm Professor Melko, Chemistry PhD, and today we're going to do some practice problems on periodic table terms, abbreviated electron configuration, atomic radius, and more. So let's jump into the problems. Let's start with this one concerning terms of the periodic table. Okay, you can go back and watch my previous lectures where we go through all of this content. This video is just dedicated to solving these problems, so feel free to pause the video and try to answer these before I work them out. The first one here is gold, a main group transition or inner transition element. Okay, sort of, given away on the screen because this periodic table I'm showing has some of the sections labeled, but this first two columns are main group, the last 6 columns are main group, everything in the middle here is transition, and these ones at the bottom are inner transitions. So to answer this question, we first have to identify what is the symbol for gold. It is AU. And that lies here in this middle section of transition elements. So gold here is a transition element. Question 2 at the bottom here, which is a rare earth element? Nd, Y, P, or B? Neodymium, yttrium, phosphorus, or boron? Inner transition metals are also known as rare earths. So it's really asking for one of these elements at the very bottom. The only one that meets that requirement is neodymium. So that's the rare earth element here. Let's try some more problems. Identify this element. I'm an inner transition element with the largest atomic number. We just got done discussing the inner transition elements are the ones here shown at the bottom. They don't really live outside the periodic table. Really, they live inside this region right here. And so it's more appropriate to break the periodic table apart and fit these in there. It's just hard to show that on a page or a screen. So typically you see these inner transition elements at the bottom of the periodic table. The one with the largest atomic number, well, they increase up to 103. So the answer here should be that last one, lawrencium, atomic number 103. We've also discussed in the previous lectures this concept of atomic radius. There are trends in the periodic table that describe whether elements get larger or smaller as I move, for instance, down the periodic table. So let's identify here which of the following elements has the largest atomic radius. And here we're going to need to be able to identify what are the symbols here. Where are these elements? Aluminum, Al. It's here. Calcium, Ca. It's here. Sodium, Na, over here, and rubidium, Rb, down here. So, to identify which has the largest atomic radius, we either need to recall the trend, okay? Things get larger going down, and things get larger going to the left. Remember the reasons for this. As I go down the periodic table, I'm adding more shells of electrons, further and further out. So the atom is getting bigger because it has more electrons and places those further and further out. Okay. As I move left to right, as I'm going towards something like fluorine, all the electrons that I'm adding here are in the same shell, but I'm also adding protons, right? As I'm counting from 7 to 8 to 9, I'm adding more protons, and those positive charges pull on the electrons harder. The electrons that I'm also adding from 7, 8 to 9 aren't going any further out, they're living in that same shell. So the net effect is that the atom gets smaller going from nitrogen to oxygen to fluorine, or moving to the right, because these extra positive charges in the nucleus are now able to exert a stronger force on the certain shells of electrons. Okay, but as I go down the periodic table, I have to add extra shells, and those are further out. So things get better going down, or things get bigger going down, things get smaller left to right. In other words, things get larger right to left, and things get larger top to bottom. So for the largest atomic radius, I want the thing most to the left and most down. Here, that's rubidium. So the answer here should be rubidium. We also have talked about electron configurations and abbreviating these. So here, write the abbreviated electron configuration for phosphorus. Phosphorus has 15 electrons. I can write out the full electron configuration if I want, but for abbreviated, I know I have to count backwards, 14, 13, 12, 11, until I get to a noble gas 10. So the abbreviated configuration I know is going to start with this previous noble gas. Here it's neon. And then I have to account for these extra electrons between that noble gas and this element. After neon, I have to account for these 2 s electrons in the third row, so that's 3 s 2 electrons. I also have to account for these 3 p electrons in this third row, so 3p 3 electrons. So this here is the abbreviated electron configuration for phosphorus, neon, 3s2, 3p3. We've also discussed dot formulas, where you write the symbol for an element and surround it by its valence electrons. So how many dots surround argon in the dot formula for argon? I would write argon and surround it with its valence electrons. Valence means the outermost s and p. So argon's outermost is those 3s2, 3p6. There's 8 valence electrons. So this would be surrounded by 8 dots. I would write them the following manner, sort of going around clockwise, then pairing them up, 8 electrons total. So the answer here should be D, not 0, right? Even though it's a noble gas, it still has valence electrons. It's just, it has all the valence electrons it wants. It doesn't have to do chemistry. That's why these last elements, the noble gases here, right, are inert. They don't react because they have these full octets, or 8 electrons in their outermost shell. Lastly, try to write the abbreviated electron configuration here for Ca+. Pause the video, try on your own. First, I'm going to think about it's abbreviated, okay? So I know I'm going to have a noble gas in brackets at some point. But before I get too far along that path, I'm going to think about calcium plus. What does this charge do? Here's calcium, okay? This positive charge here essentially is a +1. We don't write the 1. If it was +2, we would write a 2, but if it's just +1, we just write plus, no 1. So this plus here means it's a +1 charge. That means I've removed 1 electron, okay? When you remove electrons, you go back 1 in the periodic table. So really, I'm not writing the electron configuration for neutral calcium. I'm writing it for calcium +1, which is the same as writing it for potassium. So really, the abbreviated configuration for Ca+ is the abbreviated configuration for neutral potassium, right? This plus charge means I've removed 1 electron from calcium. Now it looks like potassium. If it was 1-, I would move the other way on the periodic table and do scandium. Right, but it's 1+, so I move back 1 electron to potassium. So the abbreviated configuration here, I'm really writing it for neutral potassium. I still go back to the previous noble gas, so it's argon in brackets, and then I have to account for this 1 s electron that potassium has. So the abbreviated configuration for calcium plus is just argon 4s1. That's the last practice problem I've prepared. Please go back and watch the previous lectures if you're lost on any of this material. You can find that on my YouTube channel. Click above to subscribe. And every week I do office hours on Twitch. Feel free to check me out there. I can answer whatever chemistry questions you have. I do other lectures, we solve practice problems, and we talk about science news every week. See you next time.